Rajagopal, is an associate professor in civil and environmental engineering at Stanford University. He got his PhD at UC Berkeley and it was in electrical engineering and computer science. He was also a postdoc there before moving to Stanford as an assistant professor. And his research interests in power systems relate to smart distribution grids, demand response, and demand-side data analysis. So he's going to talk today about data-driven modeling of distributed energy resources. So I'll let him.
First of all, thank you everyone for having me. So the what? Oh, this, yeah, it's a little confusing to be surrounded by people in all directions. But okay, so I was thinking a little bit about, okay, what should I present in this, summer school? Because we have had like really amazing talks and presentations and lectures on stochastic optimization, on different mechanisms for learning and different ways of modeling the grid. And I decided I wanted to share something that my group has been working on maybe in this last 2-3 years. And it really started with an observation that we formed that, based on in Stanford, we created this program that connects industry, policymakers, and the faculty on the research side. And we started asking, well, why aren't, a lot of the innovations we create for energy systems, why they don't go into practice? And one of the things that became very clear, what is different about the energy system and say something like telecommunications or information systems, is that things are, of course, far more regulated in the energy system. And what that actually implies is that unless engineers slowly get involved in some way on shaping those regulations, it will actually prevent engineering solutions from having an impact. So my rationale was, okay, maybe let's see if I can share what can you do when you start to go in a journey of trying to influence a little bit of policy, and what kind of models you need, and how does the engineering experience helps you do that. That's the motive for the presentation today. It's not going to be as exciting as Florian's talk, but it's the last talk of the day, so no equations, but they'll have a lot of modeling and a lot of questions for you to think about. So the first thing I wanted to open with is, if you think about energy system transformation, it really hinges on two triangles right now. One is we have goals. Of course, decarbonization is at the top, but because we have seen all of these climate events and the sensitivity of the grid to them, climate resiliency has come to the forefront. And we spent like the past year really talking to a lot of folks in the US and Europe about what's the difference between climate resiliency and resiliency. And the main difference for those who want to work on technical problems is that with traditional resilience, you are thinking about components of the grid that have independent failure probabilities that are small, and therefore you can use certain techniques from optimization or certain strategies to prevent loss of load. So you have the n-1, n-2. The problem with climate is that it's a huge correlated event that happens in a large geographical area and affects many components all at once. The only thing is that it's super rare. So how do you counteract that is not just an operations issue. You have to start thinking long term. So that's what would be the main difference there. And the last piece is this issue of equity that has come into energy systems due to demands and pressures of society. And there, I think there is a clear need right now for us to define appropriately what is equity. We all put equity in grants and ideas and papers, but we're not talking about some mathematical definitions. If you really want to define equity, you have to go and find out what is equitable in a community, and there is a whole kind of social sciences side to this. So those are the goals, and we are trying to achieve something with those three goals. But now if you look at the actual mechanism to achieve it, it's also kind of a triangle. When I started in power systems, coming from controls and statistics, that's my own background, I used to think, oh yeah, you can go and just do technologies. There's so many opportunities to improve things through technology. But what I ended up finding out throughout the years is that there's two other major pieces. You can come up with any idea that you want, but if it is not supported by policy, so for example, in the United States, smart meter data is owned by the utility, even though it's data about consumers. So if I create a solution that depends on utilizing smart meter data, and that solution is in competition with the objectives of a regulated utility, then unless the Public Utilities Commission authorizes the existence of this third party, there is nothing that's going to happen, even though you can show that learning algorithms and hubs and so on are definitely very efficient. So this issue of policy and people's acceptance is another vertex on the triangle. And of course, the third one is what is conventionally called business models, but basically how any idea that you come up with is going to survive economically. So if I come up with an idea to aggregate energy and bid into the wholesale market, the payment mechanisms that are supported need to compensate enough to justify all the work you put into it. Okay. So as you can see, the technology and the engineering side is like a small piece of it. And this has kind of started bothering me a little bit, and I went and tried to find out how do people actually influence these things and what academics do and so on, and what kind of research you can do. And then I applied it to the area we work on, which is distributed energy resources. So basically, one thing that needs to be clear is in this energy transition, deep engineering and data science expertise is needed not just in support of designing technology solutions, but also on how you're going to do the policy and planning. And there's going to be a ton of you that 10, 15 years from now are going to be actually running the system or sitting in some organizations that regulate the system that are going to be responsible for determining what has happened in practice. Okay. So, well, but here we are in a summer school. We are all researchers, and we want to do research. So how do we set up ourselves to engage in such work? So that was the rationale, and I just wanted to set it up in advance so you have an idea of where I'm coming from. And today we are going to see how you can actually do research and at the same time answer relevant questions in this domain, and why it is very, very, very critical for folks with our background, which are normally completely absent on these discussions, to actually be involved and contributing if we want to have a chance to set up the system to be the most efficient and successful in the goals. So the presentation today has like 4 parts. I'll give you some context, which I think might have happened on Monday, but and you guys can let me know if that's the case. Then I will show 3 motifs or 3 ideas we have explored to address this intersection of policy and technology. One is about learning DR adoptions. The second is about learning DR load patterns, or how electricity is consumed after you adopt DRs. And the last one is estimating the benefits of DR coordination. We hear a lot about like, oh yeah, there's all these like real benefits and things So we had this question of, okay, how can you estimate those benefits in a simple way? So let's just start. So for the context here, what do I mean by DERs? Just devices that are being adopted by consumers, including the ability to self-generate rooftop solar, battery storage, electric vehicle charging. It can have electric range, air conditioning or HVACs, electric water heaters. But basically, I'll group this into 4 categories: your PVs, battery storage, EV charging, and flexible loads. And most of the load flexibility that we expect in the next 10, 15 years is really going to come from thermal load flexibility. So soon I'll have some places where you can get the exact numbers of what's expected. So DRs are part of this changing grid ecosystem. And this is another super important idea when we think about we are adding renewables or we are electrifying transportation. Normally, we tend to think about these issues in isolation, but you have to place it all together because everything is changing at the same time. So if I'm adding a lot of renewables and at the same time I'm electrifying transportation, what's the right way to charge my vehicles? Should I charge them at night, or should I charge them during the day? Should I charge them in fast charging or slow charging? What type of controls should I deploy? I think all of that will be influenced by this, and we will exactly see one of the analysis we did is about that. And now in this changing grid, I think for me, the 4 central issues are: first, because of the addition of renewables, we heard this whole week how the uncertainty is increasing. I would say 2 things are increasing: the uncertainty and the variability. Variability because renewables fluctuate, so even if I knew exactly what was going to happen, my resources have to have the ability to respond to fluctuations. But it's hard to predict those fluctuations, and we tend to want to do things in the grid by scheduling in advance. So that creates the uncertainty. That's on the supply side. But on the demand side, we have electrification. And basically, the basic decarbonization strategy is to say, I'm going to decarbonize the grid, and maybe I will electrify all my carbon-using demand, make everything into electricity, and then decarbonize the grid. So that means buildings, transportation, move as much as possible to electric, and then take whatever your grid is doing and make it carbon-free. With this strategy, the grid is about 35% of carbon. The rest of these resources, buildings, transportation, et cetera, is 30. You already got 65% of carbon with decarbonize and electrify. So supply side is one part of it, which is the decarbonizing the grid equation. But on the demand side, we have the electrification. And as you add those things in there, you have to now start to think about what's the consequence of adding storage and renewables in my distribution system and EV chargers on the distribution network, on transformers, and then what is the consequence of having power that can flow back, and what are the potentials given that all of these technologies that I'm adding as electrification are all normally cloud or connected in some way, so I can coordinate them and so on. So that's why I use the word ecosystem here. We have to think about the electrification side. There is a host of challenges on the distribution level as well as integration of these technologies. Okay, so I already mentioned this. So normally, when we think about DERs, I think one main usage is really, right now in practice, anybody who adopts a DR is doing it because it's going to reduce their energy cost in some way, right? Either time of use prices or solar self-generation can reduce your costs, or you can save on your gasoline from your car, or the natural gas for your heaters. They're expensive now, for example, in Europe. So you're going to adopt DERs because of that. Either that or there is a mandate from regulators saying you are forced to adopt certain technologies. That's the only reason. Nobody's going to go there and say, okay, I'm going to pay twice as much to go and get like a water heater because I like it. I mean, there may be a small minority of people that does that. Okay, so that's kind of one big goal for DERs. The second one that we are seeing that has been an emerging use case is really the protection against blackouts. So it's resiliency. So reducing your energy costs, resiliency. Of course, the hope is we give some incentives so that these technologies are attractive, that your energy cost reductions compensate you buying them, but ultimately you're getting in exchange carbon emissions reductions, right? And finally, the third element that we think is possible, but hasn't really happened at scale, both because DERs are not present at scale, but also because we haven't figured out how to solve the integration question, is actually using DERs to reduce grid capacity requirements and integration costs. Okay, so those are the main applications of DERs. And I just wanted to share some interesting projections. These were produced by the DOE, and they're all available at NREL. So here's the energy penetration increase, the energy increase first on PV from now to 2050. This is for the United States, so it's 11%. And 2050, and that's how we have now is less than 3%. Here's the energy increase due to EVs, 31% by 2050. And you can add here the increase due to electrifying our thermal loads, about 12%. Kind of interestingly matches what you get in PVs. And finally, on the commercial loads, it's about the size of your EV increases, is another 35%. Okay, so I'm adding all of this energy and, of course, power into my end points in the grid. And so, roughly adding all of this up correctly, because there's some overlap in these definitions, it adds up to 45% increase in energy consumption. Now, there is also projections on the flexibility that we expect to exist in the load. So on the residential side, we expect about 14% of the load is going to be flexible. On the commercial side, it's 3%. And then we expect some 5% of distributed storage deployment in terms of energy. So on one side, we have this increasing load. On the other side, we have projections of increasing flexibility. But in addition to all of this, in this transformation, we are also seeing the grid is becoming smarter. So we have sensors for everything. We have smart meters, smart thermostats. Essentially, all of these resources are connected in some communication network, typically ending up in the cloud somehow. And you can use all of this information for different purposes. But what's happening today, though, with all of this stuff, is that all these DERs are mostly locally controlled. So if you think about, if you acquired a Tesla Powerwall and the solar on your rooftop, how are you going to set it up? Well, the default setting that device is going to come with is minimize your energy bill for that whole month. Okay? And everybody who acquires that is going to follow the same exact rule. Okay? So all these consumers are operating autonomously to minimize their own cost. And if you generally look at the different rate structures and what's happening in practice, basically the storage is storing the excess solar and then discharging in places where you don't have net metering, or net metering is being phased out. And I think one of the issues of having local control is going to be that now I haven't really thought about that pipe that is connecting me to the supply of energy. So let's see where this takes us. So, for example, if people adopt EVs, high EV penetration can cause major grid reliability issues. I'm going to talk a little later about our study that estimated that the grid peak power in the western United States will increase by 25% if we just adopt the existing recommendations for how EVs need to be charged. Okay, so if that is pretty scary, the peak is increasing 25%, I mean I need 25% more capacity in the generation side. At the same time, there's a second question, which is, well, what happens to my transformers and the voltages in the distribution grid? And if everybody is kind of operating in this uncoordinated way, because they're all doing just their own job of minimizing their costs, what can be some of the consequences? So there's several studies looking at this. One study, for example, here estimated that the cost to accommodate EV charging in the US is going to be about $5,400 per vehicle that you need to invest. In addition to the vehicle and the charger and everything else, you need to invest to make sure that the grid capacity is available. We started to go down this path to try to understand, well, if you have all these resources, then what can happen? And here's kind of a little simulation study with all of those projections applied to a typical grid distribution system that's available. And one of the things I'll talk about today is exactly how to do a major study like this and like all the different data sources and consequences of that. So here's kind of the transformer. This is a small distribution network. And I'm just showing there all the transformers as those yellow dots. And the more transformer overloading events you get on a year, the closer, if you're overloaded all the time for the whole year, all the hours, you're going to get at 1. If not, you're at 0. Okay, so this is 2020. This is 2030 with the projection from NREL. You get 30% of the transformers need to be upgraded. This is 2035. That's 50%. This is 2040. 65% of transformers need to be upgraded. And this is 2050. You will get 81% of all transformers. And it's a similar story if you do voltage and you look at voltage violations and you're counting those, you face the same issue. Now you may say, well, what is the big deal? Maybe upgrading 81% of the transformer costs something like, somebody did an estimate. At least for California, upgrading all the transformers is something like $10 billion. It's not a big deal if you think about the amount of time these transformers last. Right now, in practice, what's happening in California is that if you want to install a charging station, say in San Francisco, you're only going to be allowed to do that in 2028 or 2026 because there's not enough grid capacity to accommodate your charger because they need to replace the transformers. They don't have labor nor the supply chain to do that. And so you can see how there's some practical constraints that you need to take into account. So DRs, great, you're electrifying, but first, if you just allow local control, you start to run into these kind of issues. And this can actually slow down our whole decarbonization and electrification process. So this, I think we just discussed. Now, ultimately, by 2050, one question we started having is, is there actually enough line capacity in distribution networks in the United States to accommodate all of this electrification? And how about if they add new uses like data centers and et cetera that use tremendous amounts of electricity? Do we have enough? And we don't really have clear answers for any of this, nor what should be the solution to a problem like this, which is like, okay, should you just go and replace all the transformers? Another issue that emerges is this observation that the renewables that are coming onto the grid, utility scale and even consumer level, but mostly utility scale, and the actual consumption are not very correlated. So here's the famous duck curve. Everyone has seen it. This is the duck curve for California, calculated by Kaizo. So they release this report every 2-3 years, and you can see the progression. And what they're plotting is the net demand in the whole state of California. And you can see that by 2020 that there's a big belly there. And now the issue with the duck curve is you need to ramp up and down your generation. That's one major issue. The second issue, which is super interesting, if you actually plot the planned grid for California, which is a law now already in the state, that duck curve belly is going below zero. And there's massive amounts of power curtailment that's going to happen. So finally, you can even have issues if a lot of people adopt rooftop solar, where the power starts to flow back, and we say backflow, and everybody's aware of it. Well, it hasn't really happened yet. When it starts happening, it's much more than a mathematical issue. It's actually a huge, gigantic, practical issue, because none of the systems we have deployed in practice have the ability to understand what's happening when power flows in reverse through most of it. This is the practical setting. So what will happen is they will say, stop deploying this, stop doing that, and basically terminate your decarbonization efforts early. So that's our second issue, poor correlation between supply and demand. So we heard about that this week as well. So for me, first one, capacity issue. Second one, poor correlation. And to mitigate these issues, flexibility can really help the grid on the DR flexibility. So this is a little picture that we came up with for a class I taught with colleagues at Berkeley. And it just illustrates very quickly what's the idea behind demand flexibility. So today we have the grid on the left, where you have demand and it's being met by some base generation that's usually fossil fuel based. You have some renewables, and then the complement of the renewables is going to be what's in red there. That's the reserves. That's what you need to ensure that the demand and supply match all the time, and typically reserves are going to be expensive gas generators in California, for example. Okay. Now you increase the renewables, you can displace the base generation, great, but then you increase the reserves. So the grid is more expensive and you're not necessarily completely fossil fuel free. Now, if instead I allow the demand to be flexible and somehow aware of the renewables, then I can start matching things up. So conceptually, that's the super simple idea. But you're going to see today in our discussion here that this is not how we are doing things in the actual grid. So what are the existing demand flexibility approaches for DERs? This is like the minimal coordination that exists right now. So one is you have these demand response programs run by utilities or aggregator companies that typically focus on one type of device. So aggregate all the thermostats. So Nest has a program like that. Or Tesla says, okay, I'll aggregate all the power walls. And in these demand response programs, users are going to be compensated for giving up control of their devices for the utility to be able to dispatch these resources to compensate any kind of price fluctuation in the wholesale market. So typically, I schedule too little power. It's a very hot day, so I'm going to dispatch some of my demand response or curtail some load, pay you for that, and balance it. Notice none of this scheme here contemplates anything about the fact that you have renewables or not, nor contemplates anything about the reliability of the distribution network. So you don't account for transformers, you don't account for voltage regulators, and nothing like that. And most of these existing strategies are all focused on one type of device and basically taking over that device for some limited periods of time, which can work if you're going to run this in the 5 hottest days of the summer. But if I have to run it every day to match my renewables, maybe that's not necessarily the best idea. Okay, so the more recent incarnation of this is called virtual power plant programs. So basically, it's the same as demand response, but now you actually supply power. So for example, if I go and aggregate actual batteries, the batteries will not just reduce power consumption and supply virtual power, but I can actually discharge the batteries and supply actual power. Or I can turn on certain generators and supply actual power. So, but other than that, they all have the same issues as demand response. They don't really are aware of reliability of the network, and they're typically you're giving up control of your device in exchange for some credits, and whether it's worth it or not is not super clear. Let's see what has happened with this whole story, and this is kind of coming to the end of our context and then trying to understand how to overcome these issues. So last year in Kaizo, on September 6th, we had the actual historical peak of electricity of all time, which was 52 gigawatts at nearly 5 p.m. Well, this was more than the scheduled dispatchable power available at the disposal of Kaizo at the time, partly because of some botched strategies in terms of having to let go of gas power plants, relying on neighbors being able to supply power through our interconnects. What happened is on this particular day, it was super hot, and the neighboring regions were also super hot, so there was no power to be exported. So faced with this, what did Kaizo do? The first thing they did was they discharged 3 gigawatts of battery storage, but that was not enough. Then they went ahead and said, look, we need to go and talk to the governor, because unless people curtail power voluntarily, we're going to have to shut down huge swaths of Kaizo, and actually we could even have a grid collapse, because we are still short of about 3 gigawatts of power, okay? So they went and kind of argued with the governor, and finally the governor agreed to use the emergency alert service, which is meant to send real alerts, like there's an earthquake, or some kids were kidnapped, or some real rare but very extreme things, to request people, because we have an extreme heat event, and you can read the message there. Conserve energy now to protect public health and safety. Turn off or reduce non-essential power, etc., etc. So after this thing was sent at 6 o'clock, at 6:30, they got 3 gigawatts of reduction. Now, here's the interesting part of this whole story. Of these 3 gigawatts, only 23% came from all of those demand response programs, the maybe 20 startups in the space of aggregating customers and DRs, the Teslas of the world aggregating their power walls. All of that is available in California. And that only came out to 30% of those 3 gigawatts. So what is happening here? What is limiting the participation? So we went and talked to a lot of these aggregators and companies, and they said 2 things. One, consumer behavior, certainly an issue. That message from the governor is different than me asking you to participate on some program where I control your thermostat and you get $10 a year. Those are 2 different messages, right? But 2, policies. The policies we set up for how resources can be recruited and operated were a big issue, are a big issue here. So this is kind of another example. So the question that we wanted to do is like, okay, you're seeing all of these issues, and can we figure out what are the elements of this next generation of DER management? We want to make sure that, number one, it doesn't overload our distribution and transmission networks. Number two, it naturally starts to match up supply and demand with the renewables. Number three, it can actually get consumers to engage and acquire these technologies and adopt them. And four, of course, you want to ensure it's kind of equitable. And the questions that we came up with before going and engineering something can be kind of conceptually and quantify, not conceptually, but can we actually quantify what are the right strategies and what's actually going on, so that when we engineer, we can take those into account. So here are some 4 questions that I'm sharing with you today, which is like the first one is, okay, the first element is you need enough DRs to be able to do anything. So how can you measure the adoption of DR technology and ensure it's efficient and equitable, and it's correctly represented in any problem that we design engineering algorithms for? That's the first question. Second question, how to assess the transmission and distribution system impact of these technologies right now, but also when the grid is changing. Third question, can you actually learn consumer behavior and how to incentivize it properly? And finally, we talked about the possibility of coordination as a solution. How can you do it in a way that, is there even the chance to do something that can at the same time take care of the self-interest of costs, but maximize grid reliability, then support decarbonization and resiliency? So these are kind of some high-level questions. And to answer these questions and provide some general guidance, we have to start to project things, because we don't really have all of these scenarios right now. So what can we do? Well, the opportunity is there's a lot of data out there, and we hear this all the time. But how many of you here have taken the time to go and see what are all the data that's available that can be used with the grid? Okay, so there's like 2 people. So I myself was on that camp of the others, and it's super insane because there's all the data coming from the grid. There's data that is locked into silos in the utility, which you can't really access unless you have some sort of relationship, etc. There is data that sits with consumers and they don't share it, or they're not aware of it. There is data such as weather, which you depend on companies that provide it. But there's also a ton of open data like traffic or Twitter, etc. And one question that always, for me, in this conversation, when you say data-driven XYZ, is, well, but what is the value of this data? I'll just anticipate a little bit of the answer. I can tell you that getting any one of these data sources doesn't result on anything very interesting. Our big learning was, it's really the combination of several data sources can help you paint the picture to answer those questions. So now I have some questions for you, and somehow it jumped to the end here. What happened there? Okay, oops. I don't want to go back. Yeah, don't worry, I don't have 100 and something slides. These are like mostly backup slides. So let me just put it back here where we were. So I have some questions here that I wanted us to spend time on, and then we can go into the actual technical things. So first, why do we want to use models from data to understand DRs? Why do you need data-driven models? I mean, this is a valid question, right? Look, grid systems existed before we had the ability to produce and record data. It's not like 120 years ago when Thomas Edison was doing the grid, there was no computer, no Excel, no Python, no data science at all. Yet he designed the grid, and Tesla as well, that worked. So why do we need data and of course models, and why, what can it allow us to do? Yeah.
Physics-inspired models can be hard to do, number one, can be difficult to come up with, and also expensive to maintain. Both difficult to do and expensive, plus the equations or the models may not always be accurate. Like you might have a data sheet that says something, but the real thing doesn't always match the data sheet.
Yeah. If I'm trying to answer the question at a high level of DERs and what's going to happen, maybe at the first order, the accuracy is important to some extent, but maybe not as much, right? But you're right that one thing is maybe there are processes which are not physics-based, right? Like people's decisions. So we will say, okay, maybe data can help us understand that. Although we are all very happy in our power systems community that every consumer is rational and utility maximizing, right? So, okay, you had some comments as well on why use models from data.
I think part of why grids work very well, or at least at the low grid levels, is that they're over-dimensioned, and you didn't need to understand everything. You just had a buffer, and I guess we're running out of that. So now and speed is also of interest. So we want a fast transition. The grid will somehow reach the limit, so it's good to understand when and where and how we might influence it.
Yeah, that's a very good point. I think as a general point is there is this transformation on the demand, transformation on the supply, and now we have to kind of figure out what's actually happening when you couple everything together. So data could potentially help us there, but even simulations could help us there if they're well done. Anybody else on this side here for why would you use data, or why do you use data on your own research as well, right? Because we started with this question genuinely. We wanted to understand the adoption of DERs. And the first question was, well, why do we need the actual data? Why can't you go and make some assumptions about this technology looks like that one? This is how it's done for automotive. Like when a car company designs a car, they don't collect a lot of data about whether that car is going to be successful. Maybe that's why they have so many busts, but that's kind of, there's a lot of knowledge already out there that you can use. But yeah, I think that for me, one thing is really to capture parts of the system that are not easy to represent. The second issue is not a technical issue, but for the people who will consume your answers, for them to believe in what you're doing, it is far more believable when you use it with real data. That's the reality of it in practice, okay? Second question, okay, so now I said, okay, I'm going to use the data and learn different aspects of how DR adoption is happening and how the impact of it in the grid is going to be, and how to improve that situation. What are some kind of desirable properties for data-driven methods? Interpretability. That seems reasonable, yeah. Simplicity. Okay. Privacy. Very good. I'll throw that away. I'll show you, like, a lot of the research we did completely violates privacy. Okay. So, and I'll show you in a moment. What else? So yeah. So scalability, simplicity, I would say, are related. Yeah. Performance guarantees. Yeah, so yes, for us, yes. But out in the real world, honestly, people don't care too much about it. But it is definitely for engineering, your solutions is very important. Performance guarantees, very good. What else? Safety. When you're doing controls. If I'm just doing models, um, maybe I can think about some sort of fidelity or the ability to kind of capture. But I would say scalability, interpretability, and the third one is really what's lacking right now, which is reproducibility. All of these analyses that result on various policies and decisions, if you follow anything about the real grid and what's happening, is made on models that are closed. We have no way to reproduce those results, and you have to trust this consultant and that report. And I found that to be tremendously unsatisfying because when I went on this journey of trying to understand what's happening with DRs, that was the first roadblock I hit. It was like, oh, the DR data is not available out there. But well, there's all these reports and analyses and studies that were used by the regulators to make decisions. But none of the data on those are available. And why it bothers me so much? Because I can't reproduce some property that I see there, you know. So I think that's very, very important. Anything you create based on data, can you reproduce it? The third piece is, where do you get the data? So where do you get the data? So where do you get the data, let's say, if you are a PhD student here at DTU? Yeah.
Well, there's projects that measure certain things. If I really want proprietary data, I would contact maybe the DSO.
So you will contact, yeah.
And I think there's some surveys available, for example, on the usage of, or not electric vehicle per se, but transport data, so some governmental surveys.
So there's some open data sets out there. There's some things you get through connections that you might have. There's some things that you might produce from your own research. Now, the issue with most of all of this is that it's not comprehensive. I can't ask you today and say, can you paint a picture of what does the demand look like for every zip code or every neighborhood in Denmark or in the United States or in Brazil? This is not possible to answer right now. And now, if I want to understand, if I set up a policy for aggregating energy services in this particular way, what's the impact it's going to have? I do need to have an answer to what these load shapes that people are consuming are. Okay, so this is a big issue. And I think one of the things that we learned, which is the key for all of the things you're going to see here, is you have to become a real data sleuth. Either acquiring data sets through many different ways. So in the latest project one of my students is doing, you know, he actually went into a library and he found these old handbooks that have reliability data for utilities in the United States, that the data goes back like 70 years. But these books are not digital. So he's digitizing them, OCR scanning them, but now he produced this amazing data set, and like we have another interesting paper that shows, you know, a lot of what we know about reliability is totally not what the data is showing. So one is data sleuthing. The other one is maybe using AI and other techniques to produce the data. That's the other way. But essentially what you want is massive amounts of data so that you have a good coverage. What does a massive amounts of data buy you? Like people say big data. Why do you want big data? And then I'll stop with the questions and go into actually showing some stuff that we did. Yeah. Yeah. Any other? Huh? Yeah, that's right. So one advantage of having lots of data is that the data itself can be noisy, and yet you can make good inferences. That's why Amazon can predict what you're going to buy, because even though you're providing them noisy data, they have zillions of people and they can parameterize you to some extent, and so you can derive some statistical power. That I think is very important, because when you decide to generate your own data, you can start thinking about that. You don't have to be perfect. You just have to have enough data to overcome the noise that's embedded in there. Okay, so let's just start with the first kind of motive here. And we know that DR adoption, understanding where people are adopting and when and which technologies, is super important to understand various aspects of this journey of electrification. For example, which policy incentives worked? What are the distribution network impacts, where you're going to have to replace transformers first? What is the wholesale market potential? For example, if all electric vehicles are only adopted in Palo Alto, and Palo Alto happens to be in a non-congested transmission region in California, then the wholesale market value of that is very low. But if the EVs are adopted all throughout the state, distributed throughout the state, then it's a different story. Okay. Now, what is assumed about DR adoption is listed there. Consumers are rational. Their preferences, are, or at least you can think of the spatially aggregate preferences. I can look at like a neighborhood or a collection of people with similar preferences. These aggregate utility functions are usually a function of socioeconomics and incentives, and they are homogeneous. They can depend on various parameters, but I'm just going to assume they're homogeneous. Okay. And these two assumptions put together lead to utility maximizing consumers with homogeneous utilities. And you can have variations on the theme. You can add uncertainty, noise, this, that, and IEEE controls, signal smart grid is kind of, so many of these papers are written with this assumption. The first question we wanted to answer was, is this true? Okay, we want to verify, is the way people are choosing to buy batteries and solar, let's start with solar, which is the technology that's been there for a longer time. Can I make these assumptions, and are they correct? How is the adoption of solar happening? What's the strategy for me to answer this question? Suppose you had access to whatever data you wanted. What would be the strategy that you would use? Yeah, I can go and say, look, I can see how many solar panels are adopted in every zip code or census tract in Denmark. I know the socioeconomics. I know the incentives that are given, if maybe there is some variation in incentives. Certainly in the United States, that's the case. There's more than 1,000 different incentives, and they're all varying across different state boundaries. Then I can use this information and build a model. So that's like econometrics does that, or you can do regressions or whatever you want. Okay, now the challenge there is we don't really know where these DRs are deployed. In fact, there is a database called the OpenPV project that we found from NREL, but it is super incomplete. It doesn't really have the GPS locations of this information. So what you end up finding is you can't really map it correctly to the right census tract, which then detracts your ability to create the models that you want. And in fact, this is not just true about solar. We found that even the wind turbines, utility scale wind turbines, only 50% of them we know where they are in the world. Okay, this is amazing. We have deployed all of this, only know 50% where they are, and only 40% of solar. So we said, okay, here's a big issue, and we learned about this issue through our local utility in California, who said, oh, one of the big issues that we have is these customers are adding all this solar, we don't know where it is. Then I asked them, but look, you're giving them special rates. Yeah, but that is a paper-based documentation that goes to the state of California, and we get some notification, and we are not allowed to even look at that information. So inside the utility, there's a difference between operations and planning and consumer side. So they don't have access to this information. So it was very interesting. So two of our students, Jafan Yu and Cheng, heard about this issue, and they kind of went and tried to figure it out. And here's their solution. Let's go to Google Maps and take a look at the DTU campus. That's kind of the DTU campus. I'm going to zoom in into that one building there. It took me a little while. You guys don't have a lot of solar panels out here, which is something you should fix with your administration. But right there, you can see there's solar panels. So what was the idea of my students? Well, if we go and scrape Google Maps for all these images, I can just map all these solar panels. Okay, so they did that, and then they got their own personal credit card into the Google Cloud. Don't do that. And like $50,000 later, they had actually mapped all the solar panels in the United States. So how did they do? Well, it's fairly simple. You can take, there is these deep learning, these neural nets that have been trained already by Google, and now I think Amazon also has it. And you can just specialize them to detect solar panels. Now, the challenge is two things. One, most of these strategies for detection of objects in this type of imagery relies on pixel level detection. Now, each one of these little squares you see there is a tile. Okay, the United States corresponds to about 4 or 5 billion such tiles. If I'm going to run, and each tile is a 256 by 256. Now imagine how many times I have to run this gigantic neural net to get like every pixel level detection. So instead, what we did was to just say, train this, take the pre-trained neural net and specialize it to answer the question of whether there is a solar system on a tile. That already reduced your amount. You still have to run it 3 billion times, which would have taken 20 years. So then the students figured out, well, you can use night lights because it's unlikely people will put solar where there's no roads or lights. So that reduced it even further. And that was kind of the key to solve this issue. And yeah. The
Like on the walls. But you have rooftop, but you also have facade.
Yeah, so those you're not going to pick up here. But you could use something else like Google Street Views. Right? So there's always free data through all of these companies there if you are willing to exploit it. But so I'm going to skip a little bit the methods here because honestly, it's not super important that I explain this to you. You can actually go and read it in the paper and it'll get it. It's not mysterious. The key though was accelerating the running. Yes?
Just wondering, for utility, if they have data about the consumer's consumption,
Yeah.
couldn't they see when they install?
They could potentially detect it from smart meters, but they don't. And we don't have access to that data. Versus here, we have published on the web. Of course, Stanford didn't allow us to publish the location of every solar panel in the United States. So we did publish the aggregates of every census tract, and we make that data available, the granular data, to people who just send us like a one-pager describing what they want to do with the data. So, yeah.
Do you think also we can have a break soon?
Yeah, we can have a break.
Whenever it fits.
Maybe let's just finish this and then have a break. It'll be very quick. Huh? Do you want to? The what? Okay. I'll just. This is very close here, so let's just finish this. So once I have this information, here's kind of what we found. We found 1.5 million PV systems. The largest database is collected by the federal government. It costs $8 million a year for them to do that. and it only had, at that time, this was 2017, 1.2 million systems. So we detected more, and we had the GPS locations, which they unfortunately couldn't have because they get like documents from states and all that. And what can you do with that? So, by the way, we also tested the strategy in Germany by partnering with the university here. Yes?
Because based on the images, was the model able to distinguish between 3D and solar thermal?
That's an excellent question. So in this German example, yes, because we had to retrain and adjust the model. The US, there is not a lot of solar thermal. So it is not an issue there. But by the way, these detections are not perfect. As you noticed here, precision is 93%. So there is about 7% contamination of data. But the inferences we're going to make are going to aggregate over, it's exactly the power of having a lot of samples. So even though I have this, not perfect data, which we found that actually even the $8 million project has its own rate of precision, which was around 94% or 95%. So no matter how you collect data, there's going to be some issues. I also forgot to mention, we also measure the size of the panel. It's not very accurate, but we can make it accurate at the level of census tract. So the total area deployed in a tract, we were able to do it here. In the German project, we partnered with the university in Germany, and they ran this model. They actually combined it with some additional 3D LiDAR information. So there you can detect the size even more accurately individually. So just to show some insights, and then we will take a break. The first thing we decided to do is let's plot the trends of what's happening with this information. So for example, here is the average daily solar radiation and the number of solar systems per 1,000 households. I'm always going to deal with census tracts, okay? And you can see there that if the solar radiation is below 4.5 kilowatt hour per meter square per day, there isn't much deployed at all. And if it's above that, then you progressively kind of increase, which was super interesting. Many years later, talking to somebody at Sun Power, they told me, yeah, we have some sort of threshold for that. Like we only enter into markets where there's a certain radiation and on average and so on and so forth. So something that they were implementing in there. So by the way, this is not there in any economic model that has been done up to the point of this paper. This kind of effect of thresholding was not considered. The next thing we did is let's plot it against average household income. Look at that. You can see, of course, most adoption happens at higher incomes, but there is a saturation effect. Similarly with population density, the more dense you get, in the beginning you get more adoption. After that you get that decay, and who knows why that is happening. In super dense areas, why is it less? Not enough rooftop is one part. We found actually even controlling for rooftop, these average income is much worse in more dense areas. Less dense means wealthier people. So, but to end here, and we'll continue after the break, this figures here already violated the basic model that was used for measuring and the utility function that was calculated for adoption of solar, which assumed that it is linear on every variable, density, irradiance, household income. And here we just did a plot and saw it's not linear. Yes? Yeah, so I didn't show here. We do the detection for residential versus commercial because we connected it to a building footprint data set. Initially, we did one ourselves, but then Microsoft has released this, like every building in the United States, their footprint, and you can figure out by the size of the footprint fairly accurately. It's not perfect, but you're right. So, but very good point. Yeah.
I was just wondering, are you working a lot with OpenStreetMap as well? Like in Germany we do, and it's pretty well mapped, but I could imagine that in other countries it's different.
Yeah, we are doing a project now with OpenStreetMaps because we were started mapping these things, and it became a thing. Like there's like 4 or 5 things we map: solar, wind, and the distribution grid. And what we are doing with OpenStreetMaps is to try to have one model that can try to map everything or things like that. But OpenStreetMaps in the United States, it's not as rich as in Germany. But even in Germany, we found for wind turbines, for example, where there is a rich annotated set, once we ran the actual mapping for wind turbines, we found maybe some 8 or 10% more than in OpenStreetMaps. That's not a big number. We ran the same in China. We found more, like 40% more than their one public database that's available. Okay. Yeah.
One thing about the household income and the solar panels. So my understanding is that the price of solar panels decreases over time, and if you control for the purchase days of those solar panels, this might shift towards solar.
You guys are very smart. So 2017, we didn't have the date of installation. We only had the static endpoint. It took us 5 years to figure out how to do the date of installation. So last year, we published a paper with the date of installation, and that was what I was going to show next. But let's take a break so that everybody can have some water and so on, and then we come back and look at this. Okay, so I think the break is over. Let's just pick up, and I'll pick up speed here so we can go through the different motifs. So once we saw this nonlinearity here, we built our own predictive model for adoption. So this is another interesting thing that you have to differentiate, which is normally most utility function models are not predictive. They're just prescriptive. So they take all the data, they fit the regression, and they give you some confidence intervals. But if you go and get like some new user, there is no guarantee that that utility function applies to him. That's the standard in the literature in solar. And we decided to do a predictive model because the theme of the paper was in machine learning. And what we realized was there's like this thresholding effect of solar is super important, and I think it also shows up in other DR technologies. And so we had to do a 2-stage model. In the first stage, we go for the census tract and we query whether, is this place going to have solar, yes or no? That's the thresholding. Once you say yes, then you can regress the actual number of solar panels to the various socioeconomic variables like it's done in traditional models. We get an out of sample R square of 0.72. This is kind of in sample R square of various published papers at the time. And this was just, we wanted to illustrate that such data has value because the amount of data we have allow us to learn a better model. So that was kind of the interesting thing. The next thing we did is like, this picture we had was static. So it ended in 2017. But if you want to say anything about adoption, you need to know when it happened, because then you can correlate to the time when policies and incentives are given or enacted in a particular location. So how do you do that? Well, here's kind of the challenge. This was 2017. We see a solar panel on a rooftop in a home there. Okay, here's the sequence of images in the satellite for that same location. And you can see the problem is the resolution of those images is different than 2017. So you have to figure out how can you detect. So if you just went and took the train a method to detect solar and run it on every year, it does very poorly. So what we did instead is, a form of change point detection, because what we can do is we know there is a solar in 2017. I can compare this image to the other ones here. And as soon as I start to see a signal that there, a good correlation, that correlation should get reinforced for every year afterwards. Okay, so that's the simple idea. Implementing it and figuring this out took a little bit of time for us, maybe 3-4 years, and you can implement it using this thing called the Siamese neural net. I'm gonna skip this. The basic idea is you use 2 image detection neural networks, and then you can do the cross correlation between the images. So you're correlating exactly like comparing an image to any image in the sequence. So here's the accuracy. So we measure accuracy as integer numbers, and you can see that for about 86% of all of the images that we had, all the systems that we had the exact predicted year. So our prediction is exact to the year. And then if you allow 1 plus or minus 1 year, then that number goes to 90-something percent, 97% or so. So here's kind of a video of the deployments in LA and San Mateo. So San Mateo is in the Bay Area, where I'm from, and LA, of course, is in the Southern California. And you can see how that is evolving over time. Now that you have that, you can ask this question of, okay, what is the adoption look like? And the usual approach, there's several approaches to do this. One of the favored ones in this particular area of PV adoption has been the BAS model. So what we decided to do was take every census tract and fit this function, the BAS model. The BAS model just models the probability at time t that I will adopt that technology. And that probability has 2 components. One is a constant, which is like the innovators will keep adopting no matter what. And the other one is proportional to the total number of adoptions that have happened so far. So it's like a stochastic process. And it's very well known. Fitting and all of this is pretty standard. Now, what was interesting is you have a BAS model for every census tract in the US. Now I can start to ask questions about, for example, the saturation level. Adoption is saturating at different levels in different locations. What drives that? What are the socioeconomic characteristics that drive that? So here's kind of an example of, we took the different census tracts and stratified them by income. So they have different panels for each income type. And for each year, I'm showing what share of the census tracts is in which range of the BAS model. Before the adoption actually happens, that's pre-diffusion. Ramp up is when it's kind of picking up speed. Ramp down is when it's slowing down. Saturation is when it's saturated. And you can see here that, at least in terms of numbers, low-income folks are mostly in pre-diffusion levels, and wherever the adoption has happened, it's saturated very quickly. So, and we actually have the numbers for that in the paper as well. So not only that, so what we found is if you look at income, not only high-income people end up adopting more solar, they saturate at higher levels. The speed of adoption is higher, and interestingly enough, the effect of incentives is way higher for high-income folks. Even many incentives that are designed to target low-income folks. So what we, as part of the paper, we kind of went and started learning, talking to folks who work on the incentives design, and what we ended up finding out, which was super interesting, is a lot of the incentives are rebates on an income tax. And of course, if you're a low-income person in the United States, your income is really low. You don't really have anything to rebate. Whatever rebates you could get, you're already getting anyway from the government, from the federal government. So that solar rebate is not going to do anything for you. And those rebates require you to put the money to buy the solar system up front. So the one incentive that works really well, the class of incentives that work really well, is called the performance-based incentives, and those just give you an incentive based on the total kilowatt hour of production of solar. Okay, so through this study, we were able to be, I think we're the first paper that spotted this phenomenon and said, oh yeah, if your goal is equity or having lower income folks adopt solar, it really, really matters how you design those rebates and the exact way it's applied. And actually, we can show you with the data. Okay, so the last thing I want to show you on the same vein was we had a student come for a summer internship from Tsinghua, and he was like, okay, I want to map something different. And then we said, okay, there's like this, we had this idea that there's something about distribution networks. For some reason, in the US, no utility wants to share that data with you. It's so stupid because everybody can see all these lines. You know where they are. I mean, what is the big deal? Everybody knows where the substations are. So it's just some I don't know, idiot thinking that people have. Okay, so we were like, we wanted to be able to place the solar on a distribution network to start to see, oh, how much solar is flowing through a particular transformer. And I initially wrote to many utility partners of Stanford, and none of them could share the data. So that summer, a student came. We had this idea of doing street views because you could see in the street view the lines and the poles. But the problem is you can't see the connectivity. But here's kind of his amazing discovery in the first week is if you actually look upwards, Street View actually has the photo upwards, and you can see the lines there. And then it just becomes like a simple game of detect the lines and create algorithms that connect the lines together between the different images. And you can actually map the overground lines. To our surprise, we were also able to, by using OpenStreetMaps that has all the map of the roads, using that information and the existing overhead lines, we were able to kind of predict where the underground lines are. And there were some data sets that allowed us to validate that. So we have this method. It's again published. By the way, all the code and the data for all of this, it's all on GitHub online. Any one of you can go download, play with it, do whatever you want. And if you're not able to, let us know and we will figure out what's going on. So with this method, we showed that you can actually train the model in California and run it in various countries in Africa, for example, and still map the distribution grid, which is a huge deal. They don't really have that today. And finally, we started combining it with things like the tree maps and fire hazard maps and finding things like this. If you look at the undergrounding ratio, which we defined as what percentage of the miles of the distribution line are underground for a census tract, and I plot it against income, that's this plot here, and I stratify it, those different colors refer to different threat levels, low, medium, high. You can see that higher income folks have more undergrounding. And in fact, it's completely uncorrelated to the fire threat level. So why does this happen? Is PG&E, for example, actively acting against poor people? No, it's just the way the grids are designed and deployed. If you want a line undergrounded in your neighborhood, you have to get together and make a request to PG&E and send mail and do this and that. And who does that? Well, wealthy people have people that do that for them. But the rest of us don't. So we don't even know that you have to do that, right? So that result is exactly this picture there. And it's amazing. Even the tree trimming, you can see there, that's the fraction. The other panel is the fraction of lines that are intersecting with the tree cover within the IEEE safety distance. So you can see it's higher for low-income people. in this particular paper, we then turned this into an optimization problem where we detected what are the critical locations where you should bury lines in California so that you could, maintain the power flow where you have the highest risks of fire, and then how to share the cost for doing that. And the mechanism we suggested just builds on an existing mechanism that says you can share the cost either in the base rate, so everybody pays, but then wealthy people burying their lines, why should everyone pay for that? Make no sense, because the percentage increase of our bills is going to be much higher than what they face. So what the mechanism says, if you're in an area where the average income is below $100,000, then share. If you're above, you just do a local sharing. So the cost sharing mechanism. So this is a paper that's appearing this year in Nature Energy, hopefully the end of this summer. So it just got accepted. Yeah. Yeah, so the ah so the thing that we found so far, but I don't know in the Netherlands, is that lines have to naturally follow the roads with a few exceptions because every home is in a road. So generally, if your algorithm is just kind of say, here's a super simple algorithm, take every street and say there is a line through it. This will already have like an amazing performance, like 80% accuracy or something like that. So, but then you can do a little bit more and kind of figure out, like there's some places you have crossings and things like that, and you can optimize it there. No, because that we didn't look into that. That's an open question. There's many open questions. You can see the transformers. I had this question of like, can you actually detect, they're old and where they are, and somebody can create a map for the US or anywhere in the world for that. That would be amazing. So I think the potential, of course, this is just these data sets, and there's more data sets out there now. Like there's LiDAR data sets that are becoming publicly available. There's different types of satellites that are being deployed. So next year, there's going to be a high resolution thermal satellite imagery available. So you can do, for this building, you could potentially predict the exact electricity consumption at a given time of the day, or the heating or cooling consumption. That's amazing, right? Like thinking about doing that for every building in a city, it's incredible. Yeah.
Just out of curiosity, how long does it take to do, like how much time computationally does it take to go through a whole city or a whole district to figure this?
Yeah, so once you figure out the algorithms, it doesn't take very long. Like doing this thing here took maybe like a month or 3 weeks or 4 weeks. It's not bad, like doing the whole PG&E, NSE, etc. The whole research takes about, like, from beginning to end, if you want to get something to, let's say, Nature Energy, it takes about like a year and a half to 2 years, because there is the amount of time that it takes to gather the initial data. That's a huge slog. And now we have various functions that we have also published in GitHub. So you can go there, and all the functions that scrape images on this way and that way, you don't have to waste the time we wasted. But once you have that, then figuring out what you want to do, then getting yourself acquainted with the methods. But this machine learning now, I really think this is nearly fully automated. It's not like you need to be super expert, but there's still some challenges. If you're like, for the lines here, we couldn't, when we tried to just detect it on the images directly, it gave us this disconnected network. And so figuring out how to connect it, it requires somebody who likes machine learning to play around with it. But yeah, I think this is super powerful and interesting. So 2 takeaways from this part of the presentation. All these rules of thumb that people had about, like, oh, solar is adopted this way, that way, it was all wrong from what we saw in the data, which was surprising to us. But we did publish with some of those people who made those claims, so they also acknowledge it was not good. And second, I think, I'm generally very wary of all this hype on AI and all this because it's like I don't understand exactly the meaning of it. But here's one thing that's very clear. These methods that can detect objects, computer vision, they're very advanced right now for sure, and you can produce a lot of information from them. Same for text. In fact, we are having a freshman student who is running a model to detect, we wrote to various cities in California and got all their city permits, construction permits, and we want to map out where are they deploying heat pumps, where is gas heaters are being deployed instead of a heat pump. Where are you deploying EV chargers? So we already have an example where we detect way more EV chargers than the most complete data set available in the US just by doing this for like 3 months. So you can do this for so many things, and it's very, very interesting. And of course, if you can also learn from the data if I was doing a model today about, how users will adopt these technologies in these hubs, smart hubs, I'll start to take into account the fact that, well, income is a huge driver. Therefore, technologies are going to be clustered. If I look at where solar is going to appear, they're going to concentrate on the higher income census tracts. So in my model, because normally when we do simulations of the distribution grid, we say randomly place the solar across. But that is assuming a uniform spread. But that's not the case. So that's already like an insight that you can start using. Okay, so the next thing that I want to talk about is a little bit of a different type of project. So I want to understand the load patterns of DERs. And the reason I want to do this is because I want to understand how they affect the distribution grid and also the capacity requirements of the whole power system. That's the goal. And the challenge is I need to do that not just for where the DRs are today, because for example, EVs, there isn't a lot of EVs out there, but I need to take some existing projections that are fairly believable or people are using for making decisions, and then predict what the load patterns will look like then, and then match it to the grid then, and find out what happens. So that's what we wanted to do. And so we started with EVs. And so if you look at the EV load pattern, what kind of drives it? So there's a few things. First, let's think about passenger vehicles, not fleets. Well, that person drives to different locations. So, and they have, certain preferences of where they may want to charge and how much they want to charge their car. But there's a second thing that also affects it, is what charging infrastructure is available. Do you have a fast charger? Do you have a slow charger? Do you have a charger at home? Do I live in an apartment building and I have a multi-unit dwelling shared charging system? What is available to me? And finally, the third thing that might affect it is there could be some controls. So you may think, well, there's a lot of research on charge control, on trying to shape how the EV charging is happening. I think there were some posters I saw downstairs that talk about that. But even before that, today there's already a form of control that happens. In the electric code in the United States, you're allowed to install more chargers in a dedicated site for charging. You're allowed to install more chargers than the capacity of your transformer. So if your transformer is at, let's say, a 100 kilowatt transformer, you could install, 20 10 kilowatt chargers. Because these chargers, what they're going to do is, as you use more of them, they cut their power in half or by a third so that they never violate the transformer constraint. Okay, so that's a simple form of control. But there's other types of control. It can match reduce my demand charge or cost, time of use cost, or follow the solar, so many different strategies. So all of this determines my load shape, right? The load of an EV charging session. Then I have to multiply that by millions of charging sessions over, millions of vehicles to get what is the, charging total EV charging load for California at, 2030 or 2040. That's the challenge. Just in terms of these different aspects also have different opportunities. For example, on the behavior and preferences side, you can change prices or you can change the range of the vehicle. On the charging infrastructure side, this is really key. You can actually increase the access to charging. So this was a big insight we ended up finding in this work, which was really, we don't really think a lot about the fact that if you have a charger in the workplace, that's an opportunity to charge, but that's going to make you charge the car during the day, which actually is great in California. You have all this solar, that's when you want to charge. That's actually more powerful than any of the other optimization algorithms and so on. Okay, and we actually tested it. I kind of gave away the bottom line of this. But, so three-step process, and this works for other loads as well. People are going to have to do this for every other load. But basically, one, identify what are the key drivers that drive the decision-making of the person and the formation of the load shape, and identify what are the control or influence points that you can have. So controls is signals that you can send, or you can have, access is an influence point, or prices, or a range of vehicle, etc. So we focused on these last two to start off. And here's kind of what we taught. If you look at like the existing information when we started doing this work, which was about 2 years ago, 2 years and a half ago, most studies reported that, well, residential users, tend to charge if they own a single-family home on the same way. And there's two ways this is present in the literature and also in public policy. In public policy, we all encourage everyone in California and in the United States to charge at night at home because it's super convenient to charge your car at home, so you will want to have an electric vehicle. That's how the public discourse is. And in fact, the state of California was recommending every home gets a level 2 charger. So like 19 kilowatt charger in your garage, which is insane if you think about it. But because a home has about 10 kilowatt peak power, with that 19 kilowatts is like you are adding 2 homes for your convenience of charging at night, which you don't necessarily even need that extra power. Anyway, so that's one. And in the literature itself, it's amazing that every single paper we found, all drivers are utility maximizing agents, and therefore, if we are all in Palo Alto and we all own Teslas and we are, one is Steve Jobs, the other is Mark Zuckerberg, they're all billionaires, then they all are going to have the same charging profile because we're all rational and, maybe there's some small variations. So that is what was said. We went and through a project with the state of California, we actually acquired this data from ChargePoint, which had 4 million charging sessions with 38,000 EV drivers. And the first immediate striking thing that we found is if you look through the sessions and you run some simple clustering, first you can immediately notice there's many different charging locations. So workplace, public DC fast charging, residential L2, charging at home, etc. So those are all like the different categories you have. And the next thing that we noticed is you can actually run a clustering algorithm, and we started noticing things like, first, the variation of users. There's no rational driver. So there's some guys or girls who will basically drive their vehicle and charge every day. They have to see the 100%. If they don't have the 100%, they're upset. Then you see there's some people who play chicken with their car. They go as low as possible, and suddenly they go to a DC fast charger and charge it all the way. Why do they do that? It makes no sense, right? So there is like something about human behavior. Because the amount of money you spend on charging is so low, it's like, you know, your guilty pleasure or whatnot. You're not really paying attention to this. So the way we decided to face this was, let's create a probabilistic model which allows us to charge sampling sessions from a population of users. We started with this data set from ChargePoint. And the first step to build our probabilistic model was, well, let's see if there's any pattern on the data. So we did agglomerative clustering, which is a bottom-up clustering, not top-down. So every data point is a cluster, and here every data point is a driver, and we take the average of their sessions at home and the different locations, as well as the energy, duration, start time, and the fraction of weekends. We make that into a vector, and we cluster. This is the cluster that came out. We didn't tune it in any way. This is pretty interesting. You can see the first level of clustering is whether you charge mostly in the workplace, or do you focus on public and workplace, or residential. So just workplace and the rest. And then in the rest, whether you have residential or not, and then the battery size of your vehicle plays a role, etc. So that's the clustering. And we created these 16 groups that represent different types of drivers. And in each group, you now have all the sessions of drivers on that group. A session is the start time, the duration, and the energy that the user had. And we can basically fit like a Gaussian mixture model for a session. And that turned out to work well. So that's our probabilistic model. Here's a little bit of an explanation. You can go and start, probability of section. Segment is, the location, like the type of charger, public or workplace or home, etc. DC fast charging. And so you have the probability of a group. That's one of the 16 groups. And then the probability that if you are in a particular group, what's the chance or the probability that you will charge at the workplace or at home? That's the second term there. And the first term right here is the probability of the session given you know where that person from that group is charging. Okay, and that's the model. It fit nicely. You can actually, here's like the 16 groups, just we sample sessions from the probability from the PDF for the group, so conditional on the group, and then I summed it all over. That's the load shape you expect from each group. Here's kind of an interesting, a few things here. Cluster 4 has both workplace and home charging. Can you guys see there's this big, huge peak there, like a rectangular thing? Well, that is the timers. So in the data set, people add timers because they have rates for EV charging that are cheaper starting at 9 p.m. So how do you implement it at your home? Yeah.
Yeah, maybe Olivier can finish.
Yeah.
I was wondering, so many papers I've seen so far, they mainly predict home charging, or you see these massive peaks at the evening, and we are actually modeled similarly, I would say. We also have these high peaks for work charging, but it was kind of hard to, or not kind of hard to publish, but it was also a question we got, why this is so high in comparison to all others. So
Yeah, here you can see some users are only charging at work. I can give you several of my Stanford colleagues, they think because you can charge for free, or actually you can pay for charging and get your parking for free, so they only charge at the workplace because they go and drive their car and charge there, so you get a lot of incentives for doing that, even though they have the ability to charge at home. But you can get big peaks at workplace as well. And the interesting thing here is now you can modulate the behavior by saying how much do you want to sample. So here is like I'm taking cluster number 3. Yes. Oh, sorry. The what? The 4 million is not even available to us anymore because they gave us for 3 years. But the models that we learned, which basically can generate the 4 million sessions, because we tested that ability of the model to do that, it's totally available and published and in the open. So anybody can go and download from our website that.
Yeah, because for EV forecasting, there are very few like good open source datasets.
Yeah, so on actuals, if you are just wanting like workplace charging for one location, you do have some. But this data set is definitely, the trained model is open with all the parameters, and you can generate the samples you will get from here are very realistic. But not just because we account for things like day of the week, the fact that the person doesn't charge every day necessarily, they may go a week without charging. All of that is accounted for in the details of the model. Okay. So what did we do with this here? So here's just, I'm going to show. So what I showed you was this part of the model here. Then we completed our graphical model. We treated this as a graphical model. I'm not showing it that way here, but by also building the relationship between the groups and, you know, the charging options, battery size, and energy. And then I can actually see, since I have the charging sessions located spatially to a zip code level, we were able to correlate, and we have now a model that, at least for WEC region, that's the west coast of the United States, it's calibrated to go into any census tract, and you can get the distribution, the probability vector over the different groups that corresponds to that location, and you can start to generate charging events for that location. And then you can accumulate those charging events and get a load profile for each census tract. Okay. Yeah.
So, is this model only in California data?
No, well, we initially trained it on the California data, but it's not just California, it's the West Coast. So the charge point provided us sessions all the way to Oregon, but much more sparse information.
You might like think that also sort of geographical location and infrastructure might have a large influence
Yeah, so
on charging behavior. So how well do you think this
that's a great question. So what we try to do, for example, the most obvious way this is present in the data is if you look at the data, like 80 to 90% is in high net worth census tracts. Okay, this is the reality of EVs. And so how do I model, folks who are not in those census tracts? So there's some charging sessions there. It's not like there is zero. So there's some drivers who seem to live in those locations. But it's not enough to build a model. But what we did is we combined it with the surveys that the California Energy Commission had conducted, where they asked people, oh, if there's a charger, shared charging spot, what would you do, what this and that. And because it's a graphical model, you can kind of decouple the model and do fits for the different probability density functions. So we described that in the paper. So you can take different data sets and clutch them, because I'm just trying to get the driver behavior vector of probabilities for a particular location, and I can say, oh, this location may be based on the questionnaires and surveys. It discards these behaviors and allows those behaviors. So, but that's a very, very good point. Now, this method, of course, could be applied to anywhere if you had an initial data set, or somebody could actually take a limited data set, generate the data from this model, and compare it to your limited data to see, is the generation similar? If it is similar, then the assumptions that were made are also applicable to this other location. If it is not, then you can create another model There were papers that came out around the same time in applied energy that did like similar clustering ideas to create charging profiles, but for Europe, I think for the Netherlands. So it's quite, I think it's now an acceptable way to do it. What we did was that was unique was really the ability then to project this into the different locations and then tie it with a grid dispatch. So we add this load to the net load of the WEC region, which is the 11 interconnected states in the west coast of the United States. And we dispatch that grid now as well as in 2035. And kind of the main results that we found, I'm not going to go through all of them here in detail, I'll just explain them, was super simple. First of all, the policy of universal home charging, which is having everybody charge at night, which we can easily emulate in our case because you take every user driver group and say, condition the charging location or type to be home, and it'll generate samples that are different. You know, different people, maybe if they live far away, they charge a little later, etc. Is actually the worst for the grid because it will require 25% more storage than planned by 2035 to satisfy the demand from 50%, we assume 50% EVs, okay? So that's kind of the scenario that is called universal home. Here we have many conditions. Do you have timers? You don't have timers. Do you have controls that try to optimize the load shape, you know, to match solar or to minimize cost? So we applied all of that. The one thing that came out of this, which was the biggest message, is like nothing is as powerful as just telling people to charge during the daytime in WEC. If you live in WEC, forget about charging at home, charge as much as possible during the daytime. That actually makes the grid completely feasible and with enough capacity. None of these controllers could achieve anything. All of the price designs that are fixed because they synchronize the drivers at night, they don't do anything. They actually create huge peaks at night. So we looked at various strategies now that we had this model, and that was the kind of the policy conclusion, which goes against the grain of what was being promoted. But we did this work with the California Energy Commission, so they took back that message. And the great news is, if you want people to charge during the daytime, mostly you need public charging stations. And so the incentive money shouldn't go for people to put chargers at home, which is only for themselves. And typically somebody who's very wealthy gets it. You can actually give it to install public charging stations. And if you think about public charging stations, they also are accessible for everyone, so they also address the equity issue. So it's kind of a nice story. Yeah.
So two questions. One, like a typical residential charger is about $600, and then maybe $500 to install.
Yeah.
Whereas a level 2 workplace might be $7,000 from charge point plus cost of conduit and trenching. So I wonder if, you know, does it incorporate the incentive, the difference you need to provide to do that? And then I guess the second is, did ChargePoint give you the cost of charging sessions?
No.
Okay.
We didn't work with them to promote their model or anything like that. So the time when we wrote this paper, they were long away.
I just,
So,
yeah, I mean, like, because your case of like people parking at Stanford to charge,
yeah.
they're acting rationally because it's free there. And of course, you don't have the data on workplaces that don't have charging. So, like, I wonder if the ChargePoint data set itself is skewed towards workplace, whereas they might not.
That's an excellent question. So what we did to avoid that was we did separate, like we did analysis where we took data where we saw that the user charging sessions, because ChargePoint also provides charging at home, and they also provide public charging. So we tried to focus on those segments as well. So that's a very good point. The other question that you had about whether the incentives and the financial calculations, I think that's something somebody should do. But here's my general observation from a grid engineering perspective. you look at the grid in 2035, there is this massive amounts of solar in WEC, and it's all getting curtailed. And so what's going to happen is either you're going to have negative prices or free energy during that time. So it's very natural that that's a good time for EVs to charge. If you're doing it at home or in the workplace or wherever you want to connect it, or you're using a cheap charger, because that was the other thing. We didn't really see any need for 19 kilowatt charger using this data. That's completely an absurd, like there's so many hours at night that you could very comfortable. Most sessions that we saw were 100% charged by the morning. So there's, and nobody had the 19, there's very few users with that. So the point is this alignment with solar is very useful, but it's not universal. Maybe in the East Coast is going to be different. And the second point that I was very surprised was Siobhan, who was my student, she's now a postdoc at ETH Zurich. She actually her first paper was on like working on controlling workplace charging to manage solar and transformer aging and all of that. And after seeing this result, we were like, well, basically people charge during the day. That's it. You don't need to control, optimize, or anything, because we didn't do that. Just the natural factor is randomness in the behaviors of exactly when you connect, already created enough diversity that the grid is fine. But today's grid, that's not the optimal thing to do. So one of the things we made an argument in the discussion is there's a whole literature on behavior that shows the way you coach people is what they tend to adopt for a lifetime. So if you train them to charge at night, because that's what the right thing to do now, but it's not the right thing to do in the future, then that's going to definitely create a huge problem in the future. It's like if you train your kids to, avoid sugar now, even though sugar is not terrible for them when they're young, well, they will not have problems in the future. But if you don't, then you have to change their behavior in the future. That's very difficult. So that was one of the things that we cite in some papers on that. Yes?
Would you think there would be an issue where people charge during the day at work and use that charge during the night or something for their home?
I think that's fantastic. So go on your company campus, whatnot, steal their solar and power it back. Because from the grid perspective, that's what you should do. That's like one of the beautiful use cases is like run your water heater. Actually, there's some undergrad that is coming to, that's doing a summer program. That's like a Stanford undergrad. And I was asking, why don't you do this little device that you connect your water heater to your car? So when you drive back at night, you just charge your car in Stanford, and Stanford's super wealthy, so they can afford it. Then you go back and heat up your water, and the grid is very happy. So that's all. I think that's a perfect use case. But that's, again, it's a very kind of, I don't want to generalize it all over the world. But one of the things that's the last part of what I wanted to present, and I'm going to have to skip some of the other stuff I had planned. But the fact that these transformers and distribution lines are going to present a congestion challenge for electrification is going to be the biggest driver for DERs. And interestingly enough, even from a engineering literature standpoint, we don't really pay a lot of attention to this particular issue. For example, in one transformer, I have several homes. If every home has an EV charger, well, I have to replace the transformer because I don't have enough capacity typically. This is what happens in California. But then the transformer replacement cost has to be borne by the last person who did the upgrade. That last person refuses to do it. So what do? Most of them do an illegal installation. We found that like in Palo Alto, 70% of the EV chargers are illegally installed. They have a switch that connects their dryer to the same kind of the same outlet as the EV charger. And when you're not drying your clothes, it's the same amount of current. You can use it for your car. and you didn't do any upgrades, you didn't have to replace a transformer, I don't see anything wrong. The people in the city were like shocked, and they're now doing a $200 million investment program to upgrade the whole network because of this. But my point is, this kind of issues are very, very interesting because it's in communication networks. One of the big things that allowed it to grow as fast as possible is that you can oversubscribe all the infrastructure. I can put way more 1 gigabyte data plans than my cell phone tower can handle. And if you have the World Cup final, most people are going to get a super crappy image quality. If not, it all works fine because most of us are not using it at the same time. So that is not really made it all the way to the power system side, I think. So the last thing I wanted to talk about, we did a lot of work which surprisingly was the same about learning consumer behavior at the smart meter level. So we are now looking at all the loads, and they don't have EV charging or solar. And we found various interesting insights. So we took smart meter data and we analyzed it. We created this tool called Wisdom. This was all in 2014 to 2016. And we found things like this. For example, you look at cooling sensitivity, which is the kilowatt hours regressed against temperature, a measure of temperature, heating degree days and cooling degree days. And we have these million users in California. We have the data for all of them. San Francisco, people don't have air conditioning generally because it's very cold. Palo Alto is very warm, and people do have air conditioning. So that the normal models that people have used say everybody in San Francisco has no air conditioning. So forget about demand response where you send a turn-off signal to a Nest, because there is no Nests in San Francisco. And everybody in Palo Alto has a Nest because you have an air conditioner. First, we found that's not true. We actually detected there was like a substantial number of people in San Francisco that have air conditionings. And more interestingly, the cooling rates were independent. If I took any census tract in California for which we had data, the distribution of cooling rates, if you have air conditioning, is the same. So you're rich or poor, that's what we found, which is surprising. That's nothing to do with what's known in the literature at the time. So we published this. Now, how do you use this? Sorry, so the next thing we did was a super simple clustering. We ran a clustering over the load shapes of all these 66 million customer days. The California guidelines for planning say every residential customer is a dual peak, something like this here. They are a peak in the morning and a peak in the afternoon. And that's what is in the plan. That's what was used to do the projections of how electrification happens. That's the basis of the whole thing. Well, we found 200 different patterns. You have patterns like this one, nighttime peak. And because we excluded any users with solar, this is actually, graduate students at Stanford. Basically they're in their dorms, working on homeworks and all of that during the night. That's them. Or you have completely flat. That's like faculty, right? Nowhere to be found. That's the usual. Or you have single peak. So, and in fact, when you look at these dual peak things, sorry, there was some mistake here. I shouldn't have. There's only about 14% of all load shapes were dual peak. So that was a big, insight into behavior. We then built, how to create the same clustering mechanism. Surprisingly, the same thing I ended up using later on EVs. Very similar model worked for the load shapes. And then the last thing I wanted to share on this, which was super interesting, was, okay, so we found these load shapes. We used it to actually explain the performance of people and demand response. And we saw that if you're the type of person that are super consistent, that have the same load shape every day, I'm Brazilian. Brazilians are not very consistent. We don't have the same load shapes every day. you could turn either way, like for demand response, right? Like if you are very flexible, maybe I send you signals, you're willing to change. And the consistent person is not willing to change. But actually, that's not the case. The consistent person gives about 30% more demand response than people who change their load shapes from one day to the next, which was super interesting as well. And it's used by PG&E and now on targeting their plans and so on. The latest work we did on this was we wanted to know if people are aware of your consumption load shape. How many of you are aware of your load shape at your own home? What does your electricity consumption temporal pattern look like? Is it a morning peak, an afternoon peak, night, dual peak? Huh? Single night peak? Okay, so one night peak there. So go and do the experiment, write down what you think and check against your meter data if you have a smart meter website access. So we actually worked with social scientists to pair surveys with smart meter data to figure out if people are actually aware of their load shapes. And the challenge to do this is we need two things. One, you need to pair a survey where we ask actual people, what do you think your load shape is, with their actual meter data. Right? And then the second thing is, if nothing changed, electricity is a thing that changes very slow. You might just have this pattern of like everybody works the same, etc. It's hard to know whether you're aware or your just default answer turns out to be right. So how do I figure that out? So you need some sort of natural experiment where things changed, and then I can test if you're aware. Because, and that was the COVID-19. So the shelter in place, we noticed it changed the load shapes of homes. Now I can ask you, what is your load shape? After a year or two of the COVID stuff, what is your load shape? Your dominant load shape. That's exactly what we did. And what we found is maybe 30% of the people got it right. Like 70% don't know. They're wrong. And actually we have, we track in the paper how wrong they are and all of that. But why is this important? Everybody talks about real-time pricing. We need to put the time of use and all those LMPs, hourly prices. Well, you don't even know when you consume electricity. How is that going to help you shape anything? It's just going to give you a random response. And a lot of work now, if you look in econ on time of use, the more recent work is saying exactly that. Like the kind of responses they're getting are counterintuitive and not efficient. So this explains why, because people are not aware. So our response to this is either you're going to have automation, which takes away completely from the hands of the person any sort of decision making on this, but it's a cost. Or, yeah.
No, it was just the automation point. I also wanted to say that I guess many papers also assume that you have perfect automation. People would decide themselves when they would react to that.
I see.
Right?
Yeah, that could be. But it's not a reality right now.
No, not right now.
Yes.
Maybe future.
Yes.
I have a quick question regarding the results of the study. So the people had their smart meter data available, so they could have checked what their load profile
Yes.
would have been, but they just didn't check.
Yes.
They didn't know.
We also did studies on how often a person looks at, for example, we installed in 50 different homes these smart sensors that tell you like your toaster is on, and what we noticed is most people use it for like a week. It's like a novelty thing. Right? Like the thing you buy on Amazon, it looks fun, and then you use it for a week, and then you never again touch it. Because they don't understand, okay, you tell me my toaster is on, my microwave is on, my washer and dryer on, how is that, what is that information? So there's a context. So what we found, like my colleague in sociology suggested, was this notion of activities. So rather than show how much appliances consume power, what about activities? Preparing dinner and this and that. And then they tested this idea of one form of demand response is asking the family to go out for a walk or have a dinner in a restaurant. Then you don't prepare anything. You turn off your home completely and you go. And there's a huge amount of demand response, right? And you're doing it healthy. And one of the students had this crazy idea called the calorie house. Calories is energy, so it's kilowatt hours. So if you can sum the kilowatt hours of your home and the calories you're spending exercising, and I can give you incentives to go out and go for a run at 6 p.m. And you can then reduce the demand in your house. And I think this kind of more creative things certainly could have much bigger impact than at least what we saw. Even in my house, I got this little gadget that I bought and installed it. And I think we never looked at that anymore. That's it. So, yeah. Okay.
So I guess in the small defense of distributed price signals, my fear with relying too much on load control is that if it's done by the DSO, especially in the U.S. where they have an incentive to build capacity, that they will not curtail when they need to have a justification to overbuild. And so I wonder if you view simpler price signals, maybe demand charge or subscription charge, as a middle ground that might still have a place.
Yeah, I am not attacking the price signal. I'm attacking the engineering solutions built around that. I think the question here should be, price signals definitely, they exist and they indicate cost, although there is questions about whether marginal price makes sense when you have a purely 100% renewables. And my colleague Omar Karudman at Stanford in the GSB, he's an economist, he's looking into this issue, for example, and seeing, okay, does it make sense? But I'm not an expert on that. But what I feel is like, what actions can you take? One surprising thing, like for EVs, for example, much more important than the EV seeing a price signal, because they need to be connected to the charger at the right time to respond to that negative price, for example. And that might mean a certain behavior from the driver, right? So that is a connection there that is not always obvious. So we are exploring with Volkswagen, what type of information we should give to the user if you wanted him to charge more during the daytime. Is it a price? Is this? Is that? But I think there is a lot. It's a really interesting topic. Now, whether you need real-time prices and how much is that going to help for these type of loads, I don't know. I think for industrial loads, it's a different story. There's a lot of capacity in one load, and it makes more sense there. But in my ideal world, after seeing a lot of like the mess of policy and consumers and dealing with them actually directly through these projects, I think it's like super overhyped that we're going to have all these signals and homes are going to automatically respond to everything. This is not going to happen. To install one battery in a home in Fremont, where we have this program where we install 20 batteries, it took us a year. You have to get this permit, that permit, and then this doesn't work, that doesn't work, and then you install everything, and the person changes their Wi-Fi password, and suddenly the battery goes offline. I mean, it's like completely insane. So simplicity will get you 80% of the way there, but those signals will be important. I don't think that, my opinion, it's not research. But you're right that loads have to participate. What's the right way? I think is an open question. So, yeah, okay. Maybe the last thing I wanted to share here, this is super interesting. So somebody took our tool Wisdom and actually they came back and worked with us. There's this company called Ohm Connect. That's one of the largest aggregators now that aggregates loads on residential consumers, and they bid into the wholesale market in Kaizo, for example, And basically, they reward their customers for participating in demand response. And they gamified that a little bit. And their question was this: who is actually offering kilowatt hour reductions? Because a lot of this is dependent on baselining. Who is offering kilowatt hour increases? Because there are several users that don't respond, but they actually are using stuff in the wrong time. So your baseline, against the baseline, which is the average of your last 10 days, you actually increase. And what they found, and using the codes here, there's various functions in Wisdom. You can actually go and take the baseline of all the loads. You can then calculate the responses. You can then compare it to different load shapes, etc., or do regressions and learn preference models. But what they found that was super striking was 20% of the participants in their system at the time, this was around 2017, gave 80% of the response. That's pretty shocking. Like, you recruit all these people, each one costs about $200 for them to recruit. And then 20% of your customer base gives you most of the response. So what we showed is, if you don't select which people you are going to actually have participate, which is what they were doing, they're making about $3 per year per customer. Now, it will take them 100 years to recoup the $300 they used to recruit the customer, because they gave, for example, a thermostat, if you don't have one, a smart thermostat, to join the platform. With the selection, you can already double that. If you then say, top 35%, then it's $12 per year. So now here's my take, $12 per year, still for $300, still 20 years or 30 years, so it's not feasible. But then Kaizo, actually FERC proposed this ruling that says, okay, let's give some capacity market payments for demand response participants. If you add all of that, then you can recoup your investments in about 3 years if you select the top 30% of your users. So one of the things that we learned through this modeling of the load shapes was that it's very important to really select carefully who participates in demand response. And if you look at the models that we have for demand response algorithms, we don't really assume people can actually use more, or that only a small percentage of them are the right ones that are going to give the response. Now, the interesting thing here, it doesn't mean that the other 80% are doing nothing. It's different times, it's a different 20%. But in any event, it was always about 20% of the people giving the response. So how do you dynamically figure this out can really improve? Because, for example, some people that are resulted on an increase, they showed us emails that they wrote to the company saying, I did respond to your demand response request, but you claim I got no points for my participation. And then they looked, it's because their baseline was something, their actual consumption was higher, and even if they turned off light bulbs and whatnot, didn't compensate enough. So there's all kinds of issues there as well. So, okay, so takeaways: consumers are heterogeneous and seldom rational, particularly residential consumers. So commercial customers are totally different, economically motivated, and they have the ability to optimize. Data-driven models can provide the basis to build correct representations. Aggregation of DRs often results in unfairness, like in this demand response example. So kind of figuring out how to do fair or load balancing in DRs, I think is a super interesting research direction that this work supports. And simple directives can be more impactful than advanced controls in many cases. And I would love to see more studies where the baseline comparison is not do nothing, but instead of your advanced optimal control, what if you just had everybody do some simple thing, like everybody charges during the day, for example. And that would be a more fair comparison and provide a lot more understanding of how do you get to the advanced control. You need to go through some stages. Okay. The last part, Leslie, how much time do I have left? 20 minutes, 10 minutes?
10 minutes.
Okay. So I just wanted to end here. This is on quantifying the DR coordination performance. And here's the strategy. So what do we mean by quantifying it? We figured out, like, okay, the first thing we want to understand for DR coordination is how can it help improve the situation of the distribution grid? Because we saw when everybody does local controls, you have all these transformer violations and voltage violations. So you need some level of coordination. Now, you could actually go and try to do research where you say, what are optimal algorithms for coordination? That's how we started. We actually implemented those. But then much later, we were asked, like, what's the value of what you're doing? It's like too complicated to understand. So we went back to the drawing board and we said, okay, we're going to create a method to quantify the value of DR coordination. And it's going to be in the following context. The distribution grid, I'm going to take many different types that are publicly available data. Many of them are artificial, some of them are real, etc. These are data that were published in the last few years by national labs, etc. Coupled to that, all of the electrification that's happening, the projected electrification. So I'm going to modify the loads in those networks to represent EVs, thermal loads, and so on and so forth. And then I'm going to say the controllable, the flexible control, the thermal load and the EV charging and storage, they have controls. I'm going to use different bookend methods to provide bounds for my control. For example, one is a centralized, complete foresight controller, so one that knows the whole future, and one person can control all the users, and they're going to control it in a way that minimizes the number of transformer violations and voltage violations. The other one, the other extreme is every user just minimizes their own bill. Okay, so those are two. In this first one, this first bookend controller, you know, where you're minimizing the voltage and transformer, because these are just like peak events, when you're not having those peaks, you have a lot of room, and so you can just allow every user's cost function to be optimized during that time. So those are the bookend controllers. And then we actually did some research, which I'm not presenting today, which was on actually implementable schemes for DR coordination, where you don't have a central person controlling everything. So it's like, how does a DSO operate when you're only allowed to have some requests from users and so on? And it's super simple, and I will mention it. So what did we do? We just built like a simulation setup where we have all these scenarios, and we got all this data and put it all into the simulation. And then we have these different networks. We run all of the electrification year over year, and we solve the optimization of how the controllable devices are going to operate. And then we evaluate various grid metrics as well as cost. So this is just like some information on the types of networks, you know, 27 to 2,400, 1,500 nodes. So you have things like this, suburb of Oakland or San Francisco. Here's the composition. You have electrification, EV, solar, storage. And basically, the general things that we track for the reliability is what is used in hosting capacity analysis in the United States. So there's standards now for that. So transformer overloading is 2 hours moving average of transformer apparent power greater than 120% rated capacity. So it's not just like any incident of power for like 15 minutes is above the capacity, but you have this definition. And voltage violation, you have 2 hours of voltage is above or below the NC limits beyond the baseline case. So here's kind of some of the results. This is the local control in the 2050 grid, so there's no coordination, so everything is getting violated. This is centralized control. Only about 30% of the transformer needs to be replaced here. Here's another interesting result. I'm plotting the average across all those networks and the scenarios and some Monte Carlo. The growth in the percentage of overloaded transformers with just local control, you get all the way to 80%. Here's your centralized controller. As you get more flexible loads, it kind of turns the corner. And in fact, at some point, you actually unviolate transformers because you're able to optimize things. If you do something here that's a causal policy because, yeah, you got all the way up to here, in this orange line, you replace 30% of the transformers. In the blue line, you replace 80%. That's a huge difference for... Now, what is the price you pay? Well, when you're doing the centralized controller, I'm focusing on reliability, so cost is not an issue. So, or maybe it's a secondary issue. What we found is the increase in cost for consumers was only about 3%. Because it turns out the right strategy that the optimization reveals is to line up what you're consuming with solar, if you have solar. And so that like saves the capacity on the transformers, it reduces the voltage fluctuations, so it's just the right thing to do. So, and it's very, very important. The second piece of and I can share the paper with you now that you know the thesis here. The second thing that we found is it's very important to have the combination of loads. So I think somebody presented the energy hub today, which looks beyond like just say storage. No, you actually have to combine the storage with solar with your flexible thermal load. Without the thermal load control, you can't get these results here. So, and we just use the assumptions of how much flexible thermal load are going to be there, the projections from NREL. Yeah. Some side benefits of this strategy, which were really cool. We also measured what is the peak load. And it turns out by doing this reliability optimization, you actually minimize the peak load. And it reduces from like 145% increase to just 120%, like, so 20% increase instead of 45. That's a lot right there. So if you think about demand response is trying to cut the peak load. But here, we didn't do demand response. We just said optimize for the local reliability and for keeping as much transformers as you can and as much voltage equipment as you can, so minimizing the upgrades, and you got for free some of the benefits of demand response. So the last thing is this gray line is our strategy that's actually implementable, so it's somewhere in between the two, so as expected. And I'm just going to end there. So just to end, in the beginning we had this statement I proposed that, okay, deep engineering and data science expertise is needed in support of policy and planning research. And you could see how in these different problems, the fact that we know how the system actually operates and what you can actually engineer makes a big difference. Now in practice, how do you get research of this type going? I think one is picking a question for which you are willing to put the time to build that data set or setting. Second is starting to aim to publish in the appropriate venues. If you look through this presentation, we focus a lot of our publications in applied energy, but Nature Communications, Nature Energy, Joule, because those are not journals I used to publish 3 years ago. I was always publishing on IEEE, and so on. But if you want to have a voice out here, and it makes a big difference. This EV charging paper got a lot of projection. Now it's part of the PUC policy recommendations. They cite our paper, and we were also part of several city hall debates. We get letters from people. It's very important feedback as well. Okay, and seeking appropriate collaborations. Now, new areas where this type of work will be sorely needed, other than, these area of DERs, huge, still a lot to do. I also think about electricity markets and what will happen when you have these multiple new entrants. There aren't good studies. I can't even answer the simple question of, is it worthwhile for an EV to have two-way charging? Because what is the market going to look like? You have to look at the market at 2030, 2040, not now. So you have to start to create those pictures and couple things together. I think it's a huge, huge issue. Similarly, for this value of inertia and fast ramping, the concern there is much on the following fact. These are all sensitive, like there's only a certain amount of need for these services. The first few batteries that are deployed take away the fast ramping financial benefits for everyone else. But it's unclear, like that you can say about today's grid, if it is static on how it is today, and I put batteries, like in Australia, Omar showed that, okay, the third battery, you know, the first battery paid itself in like 3 years. The third battery, it's like 10 years. Okay, so, but if the grid is changing, maybe suddenly all batteries are going to make a ton of money. I mean, it's not totally clear to me how, you know, all these things have to be coupled in a model and that value shown. I think it will be very powerful. And the last area is microgrids. I think we have a lot of methods, but microgrids is kind of stuck on a limbo because we don't really understand the value it can have and what are the policies that are not allowing it to be deployed as fast. For example, one of the things that we suggested in a paper that we just submitted is we found that there are no equity issues when you look at rooftop commercial solar. They're deployed everywhere. Poor or rich, they have about the same rate of deployment. I mean, the inequity is much, much smaller. So because they all are companies with capital and they don't really care, they just want to reduce their costs and they'll go and put this technology. What if you could encourage them to also create microgrids with the neighborhoods where these stores are, like a Walmart? Then you could provide resiliency services for all the residents there, which they are on their own, they're not able to adopt those technologies. But there's a lot that, you know, questions on things like that. But yeah, thank you very much. I know this was a little different than the usual presentation, but I hope you enjoyed it.
Just on the last section with coordinating the control of the DERs, I can imagine if you're coordinating a lot of resources, the problem could get quite large. Could there be any issues with the size of the problem?
Yeah, for this analysis we did here, we did have to make some simplifications to run the optimization for the largest networks. But I did ask Thomas to also just run, you know, your Groby on the full problem and let it run for weeks to check if the simplifications were okay. So I think there's some optimization algorithm issues which are different than what you would use, let's say, in real-time control, which is kind of an interesting question, which is I need to run many scenarios of the same thing, and I have this large problem, and I don't really care if it's real-time, but I do care if it's going to take me months, right? I don't want months. But I can distribute it in different ways, and I can do some simplifications because I'm doing planning. So we didn't really find anything in the literature that talks about this. So, you know, for those who are interested in looking at problems like this, I think there's a lot of, for example, we thought about, oh, you could use machine learning and kind of learn the solutions as what people advocate, but then you have to train that model. The training itself is expensive. The other thing was, well, what if you just make some simplification? We did do simplifications. For example, we do a data-driven linearization of the distribution network equations to include it here. So it's a linear program. But even for the linear program, because you have to couple all the time intervals, and you have to do at least 3 days or a week to have a meaningful response, those programs tend to be large for the largest networks. Yeah. So open question, maybe an opportunity there. Okay. Yeah.
big engineering policy opportunities?
Yeah, so what started happening as we went about publishing this work was suddenly myself or my students and colleagues in these papers started to get invited to go into the PUC or to work with the city hall or to go and provide feedback on different issues that are addressed by the papers. Because what we found is regulators are under the same issue that we had, which is they don't have the data. They don't have, and it's even worse for them, they don't have the analysis capabilities necessarily themselves, because that's not their focus to analyze all they have analysts, which are great, but not like some data scientist sitting there willing to do this work. That was one big thing. But normally, one difference I noticed is people participating in this policy I forgot the terminology. It's not a meetup, but basically where you go and advocate for this and that, or people give their opinions before a ruling is passed. Very few actual engineers, particularly with a research background, who can know what's technically possible. So somebody can go in and say this or that, like, oh yeah, all 100% renewables, and my home needs to be disconnected from the grid. But if you know engineering, maybe you're like, oh, this is not really the way you would do it. So I think when you come with that engineering insight and provide some technical feedback, they actually get to incorporate those in the way the policies are done. And this is really huge. I also noticed we started looking at like what are the successful startups in the electricity, in this type of area of aggregation, AutoGrid, for which I was an advisor, so that's the caveat there, or O-Power. All of them had some influence on some particular. O-Power succeeded because they convinced the regulator in California that if we're going to give money to incentivize the installation of smart meters, make sure that they include the analytics that benefits the users as a requirement. And that opened the door for them to succeed with their technology, but it was also very important. It's a really important point, and they understood that point because that was their research background. So that, I think, how do you get more involved in that? It doesn't really matter the fact that your PhD is purely technical, but in the United States, it's very decentralized. So for example, where I live, the utility is owned by the city, so there is a commission of residents that is supposed to supervise it. And they're constantly, nobody wants to do the utility one because it seems to be kind of boring if you don't really like electricity stuff. So they're constantly looking for people. So if you want to super commit time, you can do that. The other is to start to do your research and like, oh, I had this idea of this particular mechanism design or this type of algorithm. What is the broader insight of that? And maybe write a paper. So in Stanford, I learned a lot from this human-centered AI, HAI initiative, like this giant initiative on AI that they started. And they hired a person to take papers and write them into policy briefs. And so that anything about AI policy center became like the center of attention, and now they're kind of ahead of knowing what's going to happen and really influencing it, which I think it's important as well. So in the US, that's the stage we are at. I don't follow in close detail what's happening in Europe, how far ahead or not you are on these electrification policies and so on. But it's a huge issue and a huge opportunity to really influence things. Yeah. Okay. So if you're interested in any of this research, I will share the papers with the team here. You can write to the first author in the paper or send me an email. If you want to use the data, they generally have the link to the data, the code, and whatever was done. If you find mistakes, critiques, please send us. 3 years ago, I had never done anything like this, so it was a lot of learning. So, and it's kind of an interesting thing, and now I'm slowly getting back into like, okay, I'm gonna go back to do engineering stuff again, and we did lots of projects, but looking into new areas. But it really taught me a lot about taking this other aspect into account can be super, super useful to design things that actually people will value rather than just our research, which is useful academically, but not necessarily is going out there. So I think that was what I wanted to share. Okay. Thank you.